Now let's talk about one of the most important cloud concepts you need to understand for the AWS Cloud Practitioner exam, elasticity. In simple terms, elasticity means the ability to automatically scale resources up and down based on demand, without manual intervention. And in AWS, the service that delivers elasticity for compute workloads is AWS Auto Scaling. What AWS Auto Scaling does. AWS Auto Scaling continuously monitors your application and automatically adjusts capacity, so you always have the right amount of compute resources at the right time. You don't have to guess future demand. You don't have to manually add or remove servers. AWS handles this automatically for you. Auto scaling ensures your application stays responsive during traffic spikes. You don't pay for unused resources when demand drops. This balance between performance and cost efficiency is the essence of cloud elasticity. Scaling out and scaling in. Elasticity works in two directions. Scaling out, increasing capacity. When demand increases, auto-scaling automatically launches new instances. Example: a retail website during a flash sale. A news site during breaking news. A streaming platform during peak hours. Auto-scaling reacts by adding capacity so users don't experience slowdowns or failures. Scaling in, reducing capacity. When demand decreases, auto-scaling terminates unnecessary instances. This prevents paying for idle resources. Exam tip: scaling out means add resources. Scaling in means remove resources. Reactive, predictive, and scheduled scaling. AWS Auto Scaling supports multiple scaling approaches. Reactive, dynamic scaling. Responds in real time to metrics such as CPU utilization, request count, network traffic. Example: if CPU exceeds 70%, auto-scaling adds instances. Predictive scaling uses machine learning to forecast demand. AWS provisions capacity before traffic increases. Example: daily traffic spikes every morning. Seasonal business patterns. Scheduled scaling. Capacity changes occur at predefined times. Example: increase capacity every Friday night. Reduce capacity after business hours. Exam tip: if the question mentions forecasting or predicting demand, think predictive scaling. Reactive, predictive, and scheduled scaling. AWS Auto Scaling supports multiple scaling approaches. Reactive, dynamic scaling. Responds in real time to metrics such as CPU utilization, request count, network traffic. Example: if CPU exceeds 70%, auto-scaling adds instances. Predictive scaling uses machine learning to forecast demand. AWS provisions capacity before traffic increases. Example: daily traffic spikes every morning. Seasonal business patterns. Scheduled scaling. Capacity changes occur at predefined times. Example: increase capacity every Friday night. Reduce capacity after business hours. Exam tip: if the question mentions forecasting or predicting demand, think predictive scaling. Auto-scaling, load balancing, and high availability. Auto-scaling doesn't work alone. It integrates tightly with elastic load balancing, ELB. ELB distributes traffic across all healthy instances. As auto-scaling adds or removes instances, ELB automatically adjusts. Auto-scaling also improves high availability. If an instance fails, auto-scaling replaces it. If an availability zone becomes unhealthy, capacity can be redistributed. This makes applications fault-tolerant, highly available, resilient to failures. Why elasticity matters. Elasticity is one of the main reasons organizations move to the cloud. Cost optimization, no over-provisioning, no idle capacity, pay only for what you use. Performance automatic scaling during peak demand, consistent user experience. Operational efficiency. No manual capacity planning, no emergency scaling during traffic spikes. For the AWS Certified Cloud Practitioner exam, remember this clearly. AWS Auto Scaling is the service that provides elasticity. It automatically scales out when demand increases, scales in when demand decreases, maintains performance, optimizes cost. If an exam question mentions automatic scaling, matching capacity to demand, paying only for what you use, handling traffic spikes without manual intervention. The correct concept is elasticity, and the key service is AWS Auto Scaling. Why elasticity matters. Before we finish this topic, let's answer a simple question. Why does elasticity matter so much in the cloud, and why does AWS test it so often? Elasticity is the reason cloud systems can handle changes in demand automatically. In real life, traffic is never stable. You might have quiet hours, and then suddenly a spike because of a promotion, a new feature release, or a seasonal event. 1. Cost optimization. With elasticity, you don't have to keep extra servers running just in case. Instead, AWS scales only when demand requires it, and scales down when demand disappears. That means you avoid over-provisioning, paying for idle resources, under-provisioning, systems slowing down or failing. A simple example. If your app is busy from 6 p.m. to 9 p.m., you don't want to pay for peak capacity all day. Elasticity helps you pay for real usage, not fear. 2. Performance and user experience. Elasticity protects performance when demand rises. When traffic spikes, auto scaling can add capacity so the app stays responsive. For the customer, that means pages load fast, checkout works, APIs don't time out. For the business, that means fewer lost sales and fewer angry users. 3. Operational efficiency. This is also about reducing manual work. Without elasticity, someone has to watch metrics, predict demand, and manually add servers. With auto scaling, that becomes automatic, consistent, and repeatable. Your team spends less time firefighting and more time improving the product. 4. AWS. Exam tip, how they test this. For CLF C02, when you see words like traffic spikes, variable demand, avoid paying for idle resources, automatically adjust capacity, you should immediately think elasticity and auto scaling. So the big idea is, elasticity keeps performance stable while keeping costs under control, and AWS Auto Scaling is one of the key services that makes that possible. What is load balancing? Let's start by understanding what load balancing actually means. In modern cloud applications, a single server is usually not enough to handle all user requests. Thousands, or even millions, of users may try to access an application at the same time. To handle this safely and efficiently, applications run on multiple servers working together. Load balancing is the process of distributing incoming traffic across multiple back-end servers so that no single server becomes overloaded. Think of a load balancer like a smart traffic controller sitting between users and your application. When a request comes in, the load balancer decides which server should handle it based on availability, health, and capacity. Instead of users connecting directly to servers, they connect to the load balancer, which then forwards each request to the best available back-end resource. In AWS, this role is handled by Elastic Load Balancing (ELB), which automatically distributes traffic across targets such as EC2 instances, containers, or IP addresses. Load balancing is essential for reliability, scalability, performance, fault tolerance. It works hand in hand with auto scaling, ensuring that traffic is always routed to healthy and available resources. Benefits of load balancing. Now let's break down why load balancing is so important and how it benefits cloud applications. 1. Application availability. One of the biggest benefits of load balancing is improved availability. Load balancers continuously perform health checks on back-end servers. If a server becomes unhealthy or stops responding, the load balancer automatically stops sending traffic to it. This means users are redirected to healthy servers automatically. Failures happen silently without downtime. Maintenance can be performed without interrupting users. Load balancers also support multi-availability zone architectures, which means if one OS fails, traffic can be routed to another, greatly improving fault tolerance and disaster recovery. 2. Application scalability. Load balancing plays a major role in helping applications scale smoothly. As demand increases, new servers can be added automatically, often through auto scaling. The load balancer begins sending traffic to the new servers. As demand decreases, extra servers can be removed. Traffic is redistributed to the remaining healthy instances. This allows applications to scale horizontally, meaning they grow by adding or removing instances instead of upgrading a single machine. This flexibility is one of the core advantages of cloud computing. 3. Application security. Load balancers also contribute to security in several important ways. They can act as a first line of defense against DDoS attacks, integrate with AWS Shield for automatic protection, work with AWS WAF to block malicious requests such as SQL injection or cross-site scripting, hide backend server details from users. By sitting in front of your application, the load balancer reduces exposure and adds an additional security layer. 4. Application performance. Load balancing improves performance by distributing traffic evenly instead of overloading a single server. Benefits include faster response times, reduced latency, better user experience, efficient resource utilization. Some load balancers can also route traffic based on location, ensuring users are served by the closest or most optimal resources. To summarize for the AWS Certified Cloud Practitioner exam, load balancing distributes traffic across multiple servers. It improves availability, scalability, security, and performance. It works closely with auto scaling. AWS provides elastic load balancing to manage traffic automatically. It enables fault tolerance and high availability across availability zones. You can think of load balancing as the traffic controller of the cloud, making sure every request goes to the right place at the right time without overloading your system. Now let's take a deeper look at why load balancers exist and what problems they actually solve in the AWS cloud. At a high level, a load balancer acts as the front door to your application. Instead of users connecting directly to a single server, all traffic first goes through the load balancer, which then decides where each request should go. This design brings several critical benefits that make modern cloud applications reliable, scalable, and secure. 1. Traffic distribution. The first and most fundamental purpose of a load balancer is traffic distribution. When users send requests to your application, whether that's loading a website, submitting a form, or calling an API, the load balancer intelligently distributes those requests across multiple backend targets, such as EC2 instances, containers running in ECS or EKS, IP addresses, Lambda functions, for application load balancer use cases. Instead of one server doing all the work, traffic is spread evenly across many servers. This prevents overload and ensures that no single resource becomes a bottleneck. Think of it like a receptionist directing visitors to available staff instead of everyone crowding into one office. 2. High availability and fault tolerance. Another critical role of a load balancer is maintaining availability, even when failures happen. In AWS, load balancers can distribute traffic across multiple availability zones, which are physically separate data centers. If one instance fails, or even if an entire availability zone becomes unavailable, the load balancer automatically stops sending traffic there. Instead, it reroutes requests only to healthy targets in other zones. This provides automatic failover, built-in fault tolerance, minimal or zero downtime. From an exam perspective, remember this idea clearly. Load balancers increase availability by routing traffic away from unhealthy resources. 3. Scalability. Load balancers work closely with Amazon EC2 Auto Scaling to support elasticity. As demand increases, Auto Scaling launches new instances. The load balancer automatically registers them. Traffic begins flowing to the new capacity. When demand decreases, instances are removed. The load balancer stops sending traffic to them. This process happens without user interruption and without manual intervention. This allows applications to handle sudden traffic spikes, scale smoothly during growth, reduce costs during low usage. In short, load balancers make horizontal scaling possible and seamless. 4. Health monitoring. Load balancers continuously perform health checks on every registered target. These checks verify whether an instance or service is responding correctly, usually by calling a specific URL or checking a port. If a target fails its health check, it is automatically marked as unhealthy. Traffic stops being sent to it. Once it recovers, traffic resumes automatically. This ensures users never interact with broken or unhealthy servers. For the exam, remember, load balancers actively monitor health and automatically remove unhealthy targets. 5. Security enhancement. Load balancers also add an important security layer in front of your application. They support TLS/SSL termination, so encryption is handled centrally. Certificate management, often integrated with AWS Certificate Manager. AWS WAF integration, to block common web attacks like SQL injection or cross-site scripting. DDoS protection, especially when used with AWS Shield. By filtering and inspecting traffic before it reaches your back-end servers, load balancers reduce attack exposure and improve overall security posture. 6. Performance improvement. Finally, load balancers improve application performance in several ways. Distributing traffic evenly prevents overloaded servers. Routing requests to healthy targets reduces delays. When combined with global routing services, requests can be directed to geographically closer endpoints. Reduced latency leads to faster response times. This means users experience smoother, faster applications, even under heavy load. To summarize, AWS load balancers exist to provide traffic distribution, high availability and fault tolerance, automatic scalability, health monitoring, improved security, better performance. For the AWS Cloud Practitioner exam, always associate load balancers with availability, scalability, and resilience. They are a foundational component of cloud-native architectures and a key building block used alongside auto scaling. Now let's talk about the different types of AWS load balancers and when to use each one. AWS provides several types of load balancers because not all applications behave the same way. Some need advanced routing logic, others need ultra-low latency, and some are designed to protect or inspect network traffic. Each load balancer operates at a different layer of the OSI model and serves a specific purpose. Understanding which load balancer to choose is a key skill for the AWS Cloud Practitioner exam. Application Load Balancer, ALB, Layer 7. Let's start with the Application Load Balancer, or ALB, which operates at Layer 7, the application layer. This means it understands application-level content, such as HTTP and HTTPS requests, URLs and paths, host headers, query strings, WebSocket connections. Because it understands application logic, ALB supports content-based routing. Key strengths of ALB. Designed for modern web applications. Ideal for microservices and container-based architectures. Integrates tightly with Amazon ECS, EKS, and AWS Fargate. Supports AWS WAF for web security. Supports authentication, OIT Cognito. Handles WebSockets and HTTP/2. Best used when you need smart routing decisions, you run microservices, you deploy containers, you want deep HTTP awareness. Network Load Balancer, NLB, Layer 4. Next is the Network Load Balancer, which operates at Layer 4, Transport Layer. Instead of inspecting HTTP content, it works directly with TCP, UDP, TLS. This makes it extremely fast and efficient. Key characteristics. Designed for ultra-low latency. Handles millions of requests per second. Supports static IP addresses. Preserves the client's source IP address. Extremely reliable and scalable. Typical use cases. Gaming servers, real-time streaming, financial systems, VoIP, custom protocols, high-performance APIs. If your application needs raw performance and does not require application-level routing logic, NLB is often the best choice. Best used when you need extreme performance. You want to preserve source IP. You are working at the transport layer. You handle TCP/UDP traffic. Gateway Load Balancer, GWLB, Layer 3. The Gateway Load Balancer operates at Layer 3, network layer, and serves a very different purpose. Instead of routing traffic to application servers, it's designed to manage network appliances, such as firewalls, intrusion detection systems, intrusion prevention systems, deep packet inspection tools. It acts as a transparent gateway, allowing you to scale and manage third-party security appliances easily. What makes GWLB unique? Works with virtual appliances. Uses Genevieve encapsulation. Centralizes inspection logic. Makes security scalable and highly available. Often used in hub and spoke network architectures. Best used when you deploy third-party security tools. You need traffic inspection at scale. You want centralized network security enforcement. Classic Load Balancer, CLB, Legacy Option. The Classic Load Balancer is the older generation load balancer that works at both Layer 4 and Layer 7, but it's now considered legacy. AWS still supports it, but it lacks modern features. It doesn't integrate as well with containers. It's not recommended for new architectures. AWS officially advises using ALB for HTTP/HTTPS workloads, NLB for high-performance TCP/UDP workloads. Summary: choosing the right load balancer. Here's how to think about it for the exam and real-world design. Application Load Balancer, ALB. Think smart routing, HTTP/HTTPS, microservices, containers. Network Load Balancer, NLB. Think ultra-fast, low latency, TCP/UDP, static IP. Gateway Load Balancer, GWLB. Think security appliances, traffic inspection, firewalls. Classic Load Balancer, CLB. Think legacy option, not recommended for new deployments.
Thank you for watching. See you in the next class.